Swayam Prabha. Digital India. Educated India.
Today's class, what we will do is we will look at the mass transfer analog of the heat transfer problem that we did. Okay? And if you look at the equations, it will look like, well, everything is very similar. All you have to do is substitute Schmidt number for Prandtl number, and you can solve the problem. But there is a subtle difference when you talk about mass transfer, okay, from let us say a spherical body to a surrounding fluid, and I just wanted to emphasize that. And just to keep the arguments clear, we will talk about single solute transfer. That is, you have a solvent, okay, and in that solvent there is a single solute which is getting transferred from the solid to the liquid. Okay. So, of a sphere in a fluid, single solute. So, you have a sphere, okay, and let us say Ca is the concentration of the solvent and Cb is the concentration of the solute. Okay, and the concentration of the solute here on the surface, the concentration of the solute is Cb naught. Now, just to make my point clear, I am going to talk about concentrations in terms of mass fractions. Okay, you can either talk in terms of moles per liter, or you can talk in grams per liter or mass fraction. So, let us say Ca and Cb are mass fractions. Okay. So, basically what this means is Ca plus Cb must be equal to 1, and when you have the solute, okay, when you have B dissolving, let us say from the surface to the liquid, there is going to be a gradient of the solute. Okay, we will have a gradient of the solute concentration, which is, and let us say you are looking at the normal direction, it will be dCb by dN. That is the gradient. Now, because this relationship has to be true, dCb by dN, and there is a gradient in the solute concentration, it will induce a gradient in the solvent concentration. I can just differentiate both of this in the direction. So, basically what I am saying is this induces a gradient in the solvent concentration. That is to say, why? Because dCa by dN must be equal to minus dCb by dN. How did I get that? By just differentiating this. Okay. So, you just differentiate it in R direction, whatever it is, so you will get that. So, my point is, if there is a gradient in the solvent, then you expect a flux of the solvent, but the solvent is not really moving. So there is no flux of solvent, there will be the net flux of the solvent is 0. So on the surface the net flux of the solvent is 0. What do I mean by net flux? Convective plus diffusive. That is what I mean by net, because if I have only diffusion, then there will be a flux of the solvent because there is a gradient, okay. That means the solvent is also moving. So my point is the solvent gradient is there, so I would say look, there is going to be a diffusive flux, but as far as I am concerned only the solute is getting transferred. So net flux has to be 0. What this means is there is a convective flux induced to negate the effect of the diffusive flux, and the combined thing is 0, okay. So basically what this means is V times C A minus d dCA by dN is 0. That is what I mean, okay. So although my properties are all constant, there is nothing like density difference which is causing the velocity. This coupling between the solute and the solvent because of the mass fraction relationship is the one which is inducing the flow, inducing the velocity. So basically what I am saying is this velocity is induced, why? So that the net flux is 0, and this is what we are interested in. So this is, so velocity V is induced although the properties are constant, because I mean I am saying density is constant, viscosity is constant, everything is constant, but I still have the flow, okay. So just to repeat, solute is getting transferred, therefore there is a solute gradient. Because of this constraint I have a solvent gradient in the solvent concentration, and the net flux from the surface of the solvent has to be 0, and therefore the only way I can ensure that there is no diffusive flux is if there is a convective flux which takes care of that, and which means this is the convective flux, that is the diffusive flux, together they should be 0. So the velocity that is induced, okay, is going to be given by this. So the velocity is given by d dCA by dN divided by Ca, okay, and A is the solvent. So if you want to write it in terms of the solute, which is what you are going to be measuring, because this solvent is usually in large excess, the solute is the one which is in small, which you can measure, okay. So if you want to write this thing in terms of the solvent, so on the surface of the sphere, okay, so this in terms of Cb is going to be dCA, I will write it as 1 minus Cb times dCb by dN. Okay, and on the surface of the sphere Cb will be equal to Cb naught, whatever the concentration is on the surface of the sphere, okay. So this is going to be d divided by 1 minus Cb naught times dCb by dN. So this is something which you do not have in heat transfer, because heat transfer, if you have properties are all constant, okay, there is no question of any velocity, only heat is coming, the flux, diffusive flux is there. Now this problem is coming because I have 2 species. Imagine if you have multiple species, then the problem gets more complicated, okay. Moral of the story is, even in if you have no forced convection, there is going to be a velocity field induced because of this mass transfer, which is not the case. So, when you are trying to find the flux, the numerator of that problem, the numerator in the Sherwood number, because Nusselt number is for heat transfer, Sherwood number is for mass transfer, you will have to consider both these effects, even the flux due to the convection and the flux due to the diffusion. Okay. So, this is something which I wanted to explain to you. I mean, I am not going to go through this in more detail, but yeah. So, in Sherwood number calculation, we have to include the minus both contributions, convective and diffusive. Okay. And I think the important point which is there is this is of course always going to be positive, 1 minus Cb naught, d is positive. This gradient dCb by dN is going to tell you what is the sign of, did I do something wrong? Yeah, this is fine. Is that a minus sign? There's a minus sign here, no? dCA by dN is minus dCb by dN, minus sign. Yeah, because I've converted dCA by dN to dCb by dN. So, the direction of the velocity is going to be decided by the gradient of the concentration. If dCb by dN is positive, okay, then you have a flux towards the surface, because v is the velocity in the normal direction. If dCb by dN is negative, then this is positive. That is, if dCb by dN is less than 0, the velocity is positive. We have convection away from the surface. Okay. Now, the point is, most of the time when we are solving problems in chemical engineering, we do not really worry about this contribution from convection, because that contribution is usually very small and we neglect it. But there may be systems where you have to include that contribution, okay. Especially like I said, if people are talking about nanoscale systems, micro scale systems, small systems, you need to maybe this contribution of this velocity can be very significant, okay, and you have to include that in your analysis. So, rest of the stuff is pretty much straightforward. So, that is the reason you do not worry about including this effect. There is an assumption, there is an approximation which we are making, which is we are basically neglecting this, but at least you should be aware that there can be a velocity induced because of the concentration gradient, okay, and these concentrations are coupled because of the way they are defined, okay, and defining it as mass fractions helps you visualize this very easily, okay. So, I want to solve another problem, which is a classical problem, which is the Taylor dispersion in a circular tube, okay. So, let me explain what this problem is. Circular tube everybody understands, but what is Taylor dispersion we are going to see. So, we have the circle, okay, and you have a parabolic velocity profile, laminar flow. This is kind of similar, we did a similar problem, not exactly the same, but slightly different earlier. What I am going to do is, I am going to have a slug, this is a slug of fluid or a chunk of fluid which I am saying exists from minus delta to plus delta. This is, let us say, Z axis, okay, cylindrical, no, so r theta z axis. And in this slug, in this small region, my temperature is T0. Outside, my temperature is T1, okay. And the actual problem is that there is flow occurring, and I want to find out how does the slug, how does this chunk behave, okay, because of the flow, and how does this temperature distribution, my objective is to find what is the temperature distribution, okay. So, there is this, mod Z less than delta, temperature is equal to T0, mod Z greater than delta, temperature equal to T1. Okay, that is the initial condition, and we have flow. What we are going to do is, we are going to say that the walls are insulated. Okay. So, there is no heat flux from the wall. Now, actually this particular problem has an exact same analog with mass transfer. In mass transfer, what you can do is, you can have again parabolic profile, okay, and you have this lug, concentration C naught here, concentration C1 outside, okay, and we are interested in how does the concentration change. The only thing is here, the diffusion is going to be decided by thermal diffusivity, and here by mass diffusivity, diffusion coefficient. That is the only difference, okay. Here alpha is going to be, I mean, let us say the fluid is the same, so your Reynolds number is the same, your pipe is the same, properties are the same. Only thing which is going to be different between this species and this is the here diffusion coefficient is important, and here thermal diffusivity is important, okay. Now, yeah, and this no flux condition, what does it do? It tells you minus k dt dot n is equal to, what are the boundary conditions here? Temperature is bounded at r equal to 0, and dt by dr equals 0 at wall. Okay, I am just trying to show the analog here, because of the insulation, no heat flux. Here the wall is solid, okay. So, there cannot be any mass flux across the solid wall. The wall is impermeable, and therefore, the derivative here also C is bounded at the center, and dC by dr equals 0 at the wall. Okay. So, because of impermeability condition. Wall. So, you see the analog, and I can make it dimensionless if this is by defining, you know, C minus C naught divided by C naught minus C 1, I can do all that. So, it will in dimensionless form, this will be 1, this will be 0. I can choose things appropriately. Okay. So, if I define theta as T minus T1, divided by T naught minus T1, and C star as C minus C1 divided by C naught minus C1. So, it will be in dimensionless, this will become 1 and 0, this will also become 1 and 0. So, I mean, it does not really matter whether you talk about, so you make it dimensionless, you can and use similar scaling, the scale for temperature in this becomes 0 to 1. Now, what I want to do is we want to understand how this guy spreads, okay, and because of the flow. Our objective, okay, when you do the experiment, okay, we find that when you do the experiment, how do I do the experiment? Find that in an experiment, the slug, of course, is going to move down, okay, because of the flow, but it will also spread out because of the velocity field and because of the thermal diffusivity. Okay. The slug moves downstream and spreads symmetrically about a center plane, okay, and the center plane will be decided by, because you have an average velocity, right, this you have parabolic profile, you have an average velocity. So, in a time t, the distance it would have moved is ut, u is the average velocity, let us say, t is the time taken, you would have moved further down, but at this, keep that as the central position. Then you will see that there is, the slug has spread both front and backwards, okay, central plane. So, which is at z equals ut. This is average velocity and this is the time of the observation. So, at time t equal to 0, my slug is here. At a later time, the slug has moved. What is the distance it has moved? Average velocity multiplied by time. Okay, and at that point, the slug would have changed. It won't remain flat. We'll come back to that. And what I'm saying in the experiment, you see, this slug is. So what I'm saying is, this is the slug at t equal to 0. If you wait for a sufficiently long time, this guy would have moved further down and it would be something like this. Okay. And what am I plotting here? This is the average temperature or temperature averaged over the cross section. So, if you want to calculate the temperature and you want to average it out at a particular point, C minus C1 only I said, no? Yeah. So, 0, it is 1 here and 0 there, yeah. So, it is fine. So, you will see this is what have I drawn? I have drawn a sketch of how the temperature is going to be, not the because temperature is going to vary with R and Z. I am averaging out in the R direction. At this point, I am saying the distance it has moved is ut. So, I am looking at a plane here and you see that it is kind of symmetric. Okay. So, when you see the average temperature is very symmetric, okay, this resembles a, at least average temperature is going to be governed by something like a diffusion process or a convection or a conduction process in heat transfer. So, basically the idea is my actual problem has convection and diffusion, okay, and conduction. But if I wanted to do this prediction of this average temperature, it looks almost like, and I am talking about a situation where I am sufficiently far away from the inlet, okay, sufficiently far away from T equal to 0, it looks very symmetric, and so this resembles, this suggests the temperature is governed by a conduction process. You understand? Because if you have something, you have a solute drop high temperature, because of diffusion, because of conduction, it will go, you know, in both the directions, in the front and back, or radial spread equally in everywhere. So, this looks like it is spreading. Now, why is this surprising? This is surprising because what do you expect? What do you expect? You expect because of the parabolic profile, the slug at the center of the plane will move, this fluid element will move much more. This guy at near the wall will be stationary, he will be just sitting where it is. This guy is going to move. Okay? So, you are expecting, so since as this will induce my slug to deform, okay, there won't be, the fluid element at the center will move much more than the fluid at the wall. So, this guy would have moved. This is the temperature profile I am drawing now. Okay, this is my slug, this is my temperature, this is my temperature, and at the center it will go more and more. I am expecting something like this. Okay. So, the idea is, and what is happening is, so what you expect is that there will be a, do you understand this? Temperature is high at the center where velocity is a max. But in actual experiment, what you see is that the temperature is pretty much, you know, does not vary significantly in the radial direction. Okay. I spoke about how the average temperature varies in the axial direction, but in the experiment, temperature does not vary significantly in the radial direction. Okay. So, I mean, what you see is pretty much not a significant variation, it is almost uniform. Some variation will be there, but it is almost uniform. How do you understand this? You say that, look, this guy is high temperature, this is low temperature because of conduction in the radial direction. Because this is high temperature, this is low temperature, there is going to be conductive heat transfer in the radial direction, that is going to make things more uniform. So, what I am saying is conduction in the radial direction is important. Okay. This is due to conduction in the radial direction. Okay. So, if you did not have conduction in the radial direction, if you had very low conductivity fluid, maybe that is the case. But if you had only convection, you will say, look, this hot guy will move much more towards in the center, not in the near the wall, and you will get a temperature field like this. But what you see is uniformity, and that is because high temperature, low temperature, conduction will make it more uniform. Okay. This is the situation far downstream. Again, I want to emphasize, this is far downstream. Okay. And most of the analysis, this Taylor's dispersion relationship is valid only far downstream. Okay. Near the center, okay, or at initial stages when the time is very small, I do not expect that to be, we will discuss this, okay, for low times, for low time instance, okay, the convection effect will dominate over the diffusion effect. We are starting the experiment. So then you will see that the slug is getting deformed into the parabolic shape kind of thing. Okay. Convection dominates and the slug deforms according to the parabolic velocity field. Okay. So, I am just going to give the qualitative picture about what the physical effects are, then I mean if I have time we will start the equations. Well, no point in me just because I think you need to learn to look at the problem both physically and mathematically. If I just give you equations and you solve, life is transport phenomena is not that. You have to look at the problem in different ways. You get confused and get more clear, get confused more. So anyway, we will do all these things with equations. I am just setting the ground up. So how would you possibly think of doing an experiment? A couple of ways. You can say I have experimentally we can have a stationary fluid and I have the slug. Okay, I have stationary fluid and let us say insulated wall okay, and then I inject or do something, put some heating rod or something and increase the temperature at the center. Okay. So, this temperature becomes T0 and this temperature becomes T1. So, everywhere it is T1, initially everywhere it is T1, but I am putting some heating rod, heating the liquid for some distance. So, I got my slug. Now, I am going to start my pump and start pumping the liquid. This is one way to do the experiment. Okay. Now, we pump the liquid and again I get a parabolic velocity field. Okay. Yeah, but the point is in this problem both the liquid is stationary, temperature is also uniform and constant steady. So, when I start the pump both the velocity and the temperature will change with time. Okay. And how can I justify the assumption of laminar flow? Okay. What is the, so basically here velocity and what is it? Temperature change with time. Remember I earlier spoke about having a laminar flow and then having the slug. So, it will take some time for the velocity field to become parabolic. Okay. So, what is the time taken for the velocity to become parabolic? How do I get a measure of the time taken? It is going to be governed by the kinematic viscosity. Okay. So, if the kinematic viscosity is much more than thermal diffusivity, what does it mean? Kinematic viscosity is more means the rate of momentum transfer will be very fast, because the time taken for momentum to transfer is given by L square by nu. Okay. The time for momentum to transfer is given by R squared by nu, and for heat, time for heat to transfer is given by R squared by alpha. Kinematic viscosity, thermal diffusivity. So, what am I saying? Nu is much higher, no? So, nu is higher means T for momentum is much lower than T for heat. So, momentum transfer is very fast. So, I will quickly get my fully developed velocity field, my parabolic profile, and so it will take longer time for my heat transfer to take place, and that is one way to understand how I can possibly do this experimentally. Okay. So, here the fully developed velocity field will be attained quickly, then heat transfer will occur. Okay. So, the assumption of having a fully developed velocity field and the slug can be experimentally realized, that is what I am trying to say, because diffusion coefficients are much smaller for heat and species. Okay. So, anyway, so although I have both velocity and temperature starting from uniform values, the velocity is going to go to parabolic field much faster, let us say millisecond, and that is going to take, let us say, 1 hour. So, the assumption of a parabolic velocity field for doing the analysis of the problem can be justified. I do not have to worry about that initial transient. Okay. So, basically the initial transient can be neglected. I can neglect the initial transient. Okay. So, now, so what? Okay, let us come back to, I think guys are getting, you want to see some equations, no? So, now before I start solving that problem with the parabolic field, let us look at a couple of cases so that we can understand what is happening. Okay. See, if the fluid is stationary, what will happen? I mean, you have the slug here. I am looking at the case fluid is not moving, but I have injected the temperature hotspot. Okay. This is at T0 and this is at T1. If you were to plot the temperature as a function of Z, you will get something like this. Okay. This is the thing at T equal to 0. Now, no movement, everybody is sitting happily, okay. But there is diffusion going to take place. Because of diffusion, this hot fluid is going to lose heat to the surrounding, and slowly the temperature inside will decrease, and this sharp profile that I have drawn, it will become smoother. So this is as T increases, temperature in the slug decreases because of diffusion, only diffusion, okay. There is no this thing. But now let us complicate things a bit, and now let us say there is going to be movement, and again we will do it step by step, and that is how you have to think when you are solving a problem. Think about it, you know, when you have a complicated problem, you should not try and jump into solving the most complicated problem. Try to do a simple version, learn something, go to the next step, learn something, go to the next step, okay. So the next complication I am going to do is, liquid, okay. This is because of diffusion, okay, because of conduction. This decrease. Next complication is liquid moves at a uniform velocity, that is like a plug flow reactor, okay. Plug flow reactor, we assume velocity is uniform. Okay. So what do you expect? I am expecting, first of all, there is going to be no deformation of the slug, because every guy is going at the same velocity, okay. But this guy is going to move. So at a later instant of time, this is going to move and it is going to remain like a slug. Will it remain like a slug? No. The convection has made it move with a uniform velocity, but there is also conduction taking place, okay. And because of the conduction, you will have a similar thing. So initially it will be a slug, now it is going to be, it would have moved, okay. This is the thing, this also has some kind of a smooth profile, okay. So the movement has taken place because of the velocity. The earlier what was a sharp profile has become smoother because of conduction, okay. So if you were to look at it from where you are sitting, you have the convective flow and you have the conduction flow. If I change my reference frame to a moving reference frame, that is, you are sitting on that slug and the slug is moving at a constant velocity, what are you going to observe? As far as you are concerned, you are sitting on the slug, you are the slug, okay. You are the slug and you are moving. You are going to only observe the slug has moved, you do not really realize that you have moved, okay. But because of conduction, you will see this. So that is the connection between these two. This is in the stationary reference frame, you will get this profile. If you are in a moving reference frame, because you are sitting on the slug, the profile is going to be similar. In a moving reference frame, in a stationary reference frame, you see the guy shift and diffuse, okay. So basically, we in this moving reference frame, in a moving reference frame, I mean you are sitting on the slug, okay. Slug, I mean you see only the spread of temperature as in a stationary fluid. Okay, because you are just moving along with the slug. Now, so what do they mean by moving reference frame? This is Z, okay, and at time t you have moved a distance of ut, okay. So in the moving reference frame, I am going to define a new coordinate Z tilde is as Z minus ut. So in the moving reference frame, since I am moving along with the slug, my position Z tilde will always be 0. Z is going to keep changing, Z will keep changing, but Z minus ut is always 0. I am here at time t equal to 0, Z tilde and Z are the same, okay, and you keep moving, Z tilde remains 0, Z becomes ut, okay. Uniform velocity at a time t, slug has moved distance ut, so Z is ut. But as far as I am concerned, I am moving along with this thing, so I am at Z tilde equal to 0. So this is my new coordinate, okay, and in this again only the diffusion effects are present, conduction effects are present. In this we see only conduction effects. I think I am repeating myself, but it is okay. So now we want to go to the next step, which is the parabolic velocity profile, okay, and I have given you the physical explanation. I mean, what is going to happen experimentally we observe. So our objective now is to develop the framework and do the analysis to try and explain the experimental observation and do it mathematically, okay. So again we will write the, I will tell you what the approach is, write the energy equation, do the scaling and look at what happens at short time scales, what happens at large time scales. We are mainly interested in large time scales as you go further away from downstream, okay, and how to choose these dimensionless characteristic scales to make equations dimensionless is important, okay. That is the basically what we are going to discuss, okay.